3 6s.
That's 5.
Oh, so you used your mode. Oh, I love that. I love that. Oh, good, good, Jen. But suppose, you know what? Here's a question. Let's remove our data from this. Let's remove the data for a moment. Let's only focus on the fact that you've got the random variable column and the probability column of 1/6. FYI, this, I'm going to break it down to just these 2 columns. This thing, if you just extract those 2 pieces from over there, that's called a probability distribution. This is called a probability. And this is all we're going to be spending time in the remainder of the course, our different versions of this. I have two main versions of it after we understand what they are by definition. So this is all I'm going to spend a last bit of time. And we kind of hinted at this in 105 last term. I wasn't calling it that then, but we want to focus our study on that now. It's a probability distribution. Before it was a frequency distribution. It was the beginning of the course. X, F, X, F. Kelly, you actually use the phrase F for frequency. But if you focus instead on the probability of occurrence of the variables, we just call it a probability distribution instead. So the X column, in this case, number of pips, and the P of X column, the probability of that number of pips taken together, is just called our probability distribution. Just a phrase. I'll keep saying it. And one of the most beautiful things about a probability distribution is you can average them. You can average them. Remember how you averaged a frequency distribution? What kind of average did you have to do? You have to do a weighted average. Thank you. Can we do a weighted average here? Well, of course we can. How do you find the average of a probability distribution? In the same way you do it for a frequency distribution. You do a weighted average. You do a weighted average. You take each data point times its weight, and then you add the next data point times its weight, and you just keep doing that for as many as you have, like your GPA calculation. Same thing. And what do you divide by then? Remember what you divide by in a weighted average? Let's get the answer actually. The sum of the, what do you divide by? Do you remember? It's been, see, you did them as recently as last week. It's just that you're using your TIs to do them now, and you're not thinking about the actual calculation anymore. That's why I bring it back now. Not to be a bastard, but just to refresh your memory, to kind of scratch that and kind of bring it, let it bleed a little bit more. Not to be a gross analogy. That's pretty gross, sorry. What do you divide by? The sum of the, go ahead. Michaela, yes?
Times 0?
Yes, the frequencies, yes. But in this case, we should do some of the weights, right? The sum of the weights. Yeah, good. The number of times you roll, which is just a fancy word for frequency. Or my frequency is a fancy word for a very intuitive statement of the sum of the weights. Can we do this with the dice? Hell yeah, we can. Let's do it. What's your first data point in our distribution? 1. 1 is our first data point. How frequently does it occur? Don't ignore our data, go with the theoreticals for now. 1/6 at a time, yes? 1 times 1/6. Plus, what's the next data point? 2. Times? 1/6. It's going to get pretty boring, I apologize. Plus? 3. Times? Plus? Times? Plus? Times? Plus? Times? Plus? Good. That's the numerator. How about the denominator? What goes down there? Right, good, Eric. Very good. Just ignore our data. We're going with the theoreticals now. What do we call them, the weights up there at the top? What were we using? All those 1/6ths. It's 1, isn't it?
Yeah.
It's 1. It's 1. Because 1/6 plus 1/6 plus all the way across to the 1/6. And guess what? It's always going to be 1. Because those probabilities have to add up to 1. You see? That's the point. That's the point of the distribution is you have outlined every single possible value for the variable. So the probabilities have to sum to 100% because either that one happens or this one or that one or that one, and that's it. So the best part about it is you can just take it and ignore the bottom part of that calculation because it's always going to sum to 1. This is one of the reasons the calculation of an average of a probability distribution is superior to a frequency distribution, because Michaela, as you correctly said, we'd have to add up the frequencies and divide by that. Eric, you actually said it too. You have to divide by the frequencies. But the frequencies are now relative frequencies, which add up to 1 every single time. And that makes it easier to calculate. It also gives us one more thing I want to chit-chat about later, but not right now because you guys are still processing this. So what does it add up to? Well, let's see. 1/16, that's just 1/6, right? 1/6 plus 2/6 plus 3/6, 4/6, 5/6. That's a lot of sixths. 21/6? Yeah. 21/6 is 3.5. There's your average. On average, you roll a 3.5. To which you reply, oh, that was the response I was expecting, a little cheer. Yay. I was expecting a more skeptical / critical review, where you say, you can't roll a 3.5. But can you average a 3.5? Yes, because for every 1 you roll, somewhere else you roll 6, which add to 7 divided by 2 is 3.5. For every 4 you roll, somewhere else you're going to roll a 4 for sure. But now you roll 2 4s, but there are going to be 2 3s that offset that. And add to 7 divided by 2 give you 3.5. And for every 2 there's a 5 somewhere else that pairs up with it. I'm not promising that it happens every 6 times, every 12 times, every 18 times. I'm saying if you take all those results and put them in a line, you can reorder them so that it goes 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. It doesn't happen that way. If it does happen that way, you sell those dice on eBay for a lot of money. But on average, it does happen that you average 3.5 on average over time. And that takes some getting used to, friends. That takes some getting used to, because you have to process that right now and realize that that does not mean you're guaranteed that at any fixed point in time. You're not guaranteed that at a fixed point in time. This is over a long period of time that becomes the average. So if you watch a die being rolled in a Vegas casino, and they don't kick you out for just standing there staring at the table, you'll watch each one of those dice will average 3.5. And what's interesting is you're noticing how often they change dice in a casino. They're constantly changing dice and putting new ones on because they're trying to make sure as much precision as possible that it's maintaining that average of 3.5. That's why it keeps getting changed. As you use it, they wear down. I mean, it's a felt table, so I don't know how much it's wearing down. I don't know how much they're throwing away by doing that. But nonetheless, that's the logic behind it. Could you do a standard deviation of that as well? Of course you can. I'm never going to ask you to do it. It's silly because you have one of our stats. What do you think a standard deviation is? Plus or minus 1. So 3.5 is in the middle, yes? What do you think the average is? Or, excuse me, the standard deviation is? Plus or minus what? Ballpark. 2? 2.5? 2.5? Good, good. Let's test it. Now, you can calculate the average. I'll give you the formula in a minute. Or this, if you want the formula, I'll give it to you in a minute. Grab your TIs. Go to your TIs. We have a tool. Let's keep using it. There is a reason I ran you through that average calculation right there. I'll come back to it on Tuesday of next week once you've forgotten all of this. Let's be honest. It's going to be a long weekend. Hopefully the weather's nice for you guys. But we'll come back to it again and again and again. It's a huge idea.